Okay, welcome back. This time I want to talk about in calculus calculating volumes, but in this case using cylindrical shells rather than using cross sections. There is a difference, and I'll explain to you in just a second here. All right, so let me erase this off of here so I have a little bit of room to write. All right, so previously we were talking about volumes, and we would have a shape represented by f of x, and we would break it up and then rotate something typically around the x-axis is a good starting point. If you could rotate around the y-axis as well over here. But in this particular case, if you rotate it around the y-axis, it's only easy to rotate around the y-axis if you have some sort of shape that only has one value for x. One value for x for every value of y. But in this particular case up here, when you have a value for y, you hit here and here. And so now the problem does not get to be so easy. But luckily, the cylindrical, whatever this thing is called, cylindrical shells method, it's a little bit confusing. If you look at some of the textbooks, it's really hard for them to explain what's going on in text. You have to read it over a few times, but I'm going to try to explain what they're talking about here. So if you remember, if we were doing a typical volume here, we would start with volume equals, and then we'd have the limit as n goes to infinity, the sum of all n's starting with I equals 1, and then you would have the area as a function of x, and then delta x. Now this area right here is what houses where you're going to rotate around and what it's going to look like. If you're rotating something around, then you're going to create these, each delta x goes here to here, and that's where the x-axis comes through. You're going to create these cylinders going this way, and because you're rotating around the x-axis. And then the area that they're talking about is right here, area x. So rotating those around is great. And then your area is going to look something like dx, because it's going this way. Your f of x value is going to be right there and act as the radius. And so you're going to have something, so that area right there is going to be, let's see, pi f of x squared, pi r squared. Okay, so that's what's going to be plugged into that area right there. But now if we're talking about cylindrical shells, we are no longer talking about rotating around the x-axis, typically. We are talking about rotating around the y-axis, and we're having something that looks like this. So we're going to go around this way. Okay, and so what do we get then? If we take this as our area, we're going to get some sort of donut-y shape thing coming out and going around. Ugh, that's horrible. Okay, so it actually does that. And it's a mess. Okay, so this shape goes all the way around and creates the donut. I think this is what I was looking for right there. All right, so, but we want to do it in terms of changing x. That creeps out there. So, so we can still maintain, we're not integrating for change in y, like they have in some of the textbook examples. So things start to get tricky. So now, if you remember how to calculate the volume of two cylinders, you got donut one, inner, donut outer, comes down that way. We have a height here. We have R1, and then the R2 is the outer. So if we create the area or the volume of the outer one is going to be pi R2 squared times the height minus the inner one, pi R1 squared times the height. Okay, performing a little bit of algebra magic, we can pull out pi, oops, that's not a pi, that's pi h, and then we're left with R2 squared minus R1 squared. That can be factored. R2 plus R1 minus R1. Okay, and this is all times pi h, volume. Okay, so looking at it, that's still not very helpful. So continuing on, we look at this guy right here is the most useless term in there. There's no reason we should add that y1 or r1 plus r2. But if you think about it, that term divided by, let's see, plus r1 divided by 2 actually equals the mean radius right there, right in the middle. Okay, and then so if we divide by 2 here, we have to multiply by a 2 on the outside. Okay, and so we have 2 pi h, and then r2 minus r1. Okay, if we look at that right there, r2 minus r1, is there anything special about that? That is delta r, or if you look at it right here, it is the width of our little cylinder, our little donut here, which is equal to delta x. Okay, so delta r equals delta x. Okay, I'm going to erase that because I put that in a very bad spot. So I'll just write it down here. Oops, not ax. Delta x. Okay, so 2 pi, and the h right here. H is the height of our little donut cylinder. That actually equals f of x. So f of x. Okay, so I'm going to knock this down to the next level to match up to my delta x, f of x, and then I have the radius 2 plus radius 1 divided by 2. And if we control ourselves, we can make this value right here for the average radius using the mid value theorem. That, rather than honing in on this being my x, we hone in on the middle of that donut right there. So this is going to essentially be r, or it'll essentially be x. So volume. So hopefully I'm still on the page. So remember that. That's something to remember here in the setup. Okay, so continuing to look at this problem now, I'm going to start right here and say, okay, it looks like I've made everything completely worse, but I'm going to make it make sense in just a second here. So let me put the next board on and start with that equation again. V equals 2 pi times x, right? And then the function of x, and then delta x. Okay, and so what that looks like now is, and you can hear the airplanes going by, and that's why I kind of broke up the video before. If I put it in terms of a limit as n goes to infinity, the summation of from n I equals 1, this fits right in there now. That is 2 pi x f of x and then delta x. So now if you remember the videos from before on area under a curve or volume using the cross-section method, you have to change these x's into terms of I. Okay, I'm just doing this for example. I'm gonna pull this section out of here and use a normal integral because it's so much faster. But if you remember that in terms of I, where your delta x, because this is going to infinity, actually equals the b minus a over n, and then your x would equal, x in terms of I would equal a plus, this is where things get different now. It used to be I times delta x, okay? But if you remember what I was just showing you, we wanted to find x at the midpoint right there. So we need to change what this is a little bit. There's a couple different ways to do it. It's a plus let's see. We can start there, and then we can minus off 1/2 delta x or something. We can just figure that out algebraically. So now if you look at this problem here, we could go in and plug these in and start solving it. But it's so much easier at this point to change it over to a regular integral. Okay, so what we need to do is we need to carve out this section right there. So that's going to be 2 pi x, and that's going to be, oops, f of x right there. Okay, and then your delta x becomes your dx. Okay, and then, so whatever we have for our function, we multiply another delta x, or another x into that. The 2 pi can go out into the front, it's no big deal. And then we can solve just like a definite integral. So that's the basic gist, and I'll probably do an example on another video because I don't want these videos to be too god-awfully bad. But if you look, that is the formula that things plug into, and what I just explained to you is why. So anyway, take a look. Next videos will come out in a little bit, and subscribe to the channel so that you can actually get a notification when you get this. I'll try to follow along with the syllabus for the course so that I can give you some introduction before you actually go into the class. Good luck.